I want to thank the RQS workshop organizers for inviting me to give this talk and highlight some of the recent work at Duke with trapped ions on error correction, as well as noise, the impacts of noise on error correction, and highlight at the end some other progress and applications in the experimental platform. And I want to thank especially the students and postdocs for being here and making this workshop and RQS overall a very successful program. As I mentioned, I will be talking about the ION platform. This is a system that many of you are familiar with based on the HOA 2.1.1 trap that originally was built up under IARPA's Logic Q program at Maryland in the group of Chris Monroe. And it has worked over the years with anywhere between 7 and 27 ions, up to 25 spits. And I will be presenting work with an increased size digital system supported by this machine. Very high picture overview that's also along the lines of RQS. In doing quantum applications, we want to get somewhere interesting, somewhere where we cannot simulate classically, as highlighted in Ken's talk, and also somewhere, hopefully, that has important practical, very important practical consequences and advantages. But on the way there, also as a team of RQS, we have the problem, the enemy of errors, whether gate errors or analog errors. And some of these are technical, such as charging noise, charge fluctuations in ion trap surface charge physics. But some are more physical, spontaneous scattering, and some are truly fundamental physics, such as black-body radiation or micromotion in the ground state of the ion. And at least as far as we understand the necessary error rates for the leading algorithms, even these very low physical error sources pose large challenges in getting where we want to get in the coming years or 10 years plus. So many of us believe that error correction is a great way to bypass that, at least bypass very low errors. So if we have good enough hardware and scalable enough hardware, we hope that with error correction we can trade qubit numbers, hopefully not very inefficiently, for gate errors. In order to do this, we need to have some idea what is the interplay between gate errors and qubit demands and at various stages of the hardware development, the different error rates. So I will be highlighting at current error rates in large trapped ion platforms a comparison of two different decoders applied to a particular code. When talking about error correction in ions, a thing to bear in mind is that ion qubits and neutral atom qubits can be made very, very good. So coherence times of more than an hour have been demonstrated in trapped ions in particular. Very long coherence times are also available in neutral atom hyperfine states. So it will be very difficult to make at least atomic qubits fundamentally much better. But what we are hoping to do in atomic systems through error correction is at least to make the gates better, and especially the difficult ones, the 2-qubit gate. And various codes are suitable to various extents with various ease to help us along with realizing a better 2-qubit gate, which still remains an outstanding challenge. The code that I will be talking about is the Bacon-Shor 13 code, which is a subsystem code. It's of distance 3, which means it can correct any single qubit error. And it supports fault-tolerant encoding, gates, stabilizer readout, and measurement. It's based on 9 data qubits, and 4 weight-6 stabilizers. And we previously on the same system demonstrated the encoding and single qubit logical gates implemented fault-tolerantly on this system, using 13 ion qubits out of 15 ions. I want to highlight the encoding in the Bacon-Shor code is pretty straightforward. To encode logical 0 and 1 states, you essentially just prepare 3 GHZ states, 1 per row, which can be straightforwardly done via the native ion XX gates. If creating GHZ states, it behooves one to be noise aware. As we showed in collaboration with Ken Brown, if you're doing GHZs for your code, it's probably not the best idea to form a GHZ like that to encode your logical states, because I mean it's a good idea if you're making a magnetic field sensor or a clock sensor, but this is maximally sensitive to any changes in your offset frequency. So if meanwhile you encode into states of lower magnetization like that, we demonstrated that you can get lower errors. In order to decode the state of the code, you simply look at the parity of each of the 3 rows, and then you perform a majority vote between the 3 rows for the parity. So if the first one has parity 1, second one parity 1, third one parity -1, you will conclude that your code is parity 1, so in the 1 state. And this majority vote implements 1 round of error correction by default at the end of your circuit in the Z basis. That's always available. In order to perform syndrome readout, we need to read out these weight 6 stabilizers, which we do with 4 ancilla. And this can be done using 2-qubit gates, making use of high or full connectivity of this system to readily read out a weight 6 stabilizer. One catch here is that in order to ensure fault tolerance, if the first stabilizer readouts that you perform report an error, you need to perform a second round. So it is possible that the readout had itself an error, and that's why you got an error. So if you correct based on that, you will introduce a fault. In order to ensure higher order scaling with the probability of error, a second round is needed, which requires more qubits. So this allows a larger system. So we expanded the system from 23 trapped ytterbium to 23 trapped ytterbium-171 ions. Still on the same trap. That's required an upgrade of optics and the beam addressing system, and also some engineering of the motional modes. As you well know, this addresses the qubits using a Raman pulsed laser, which performs a spin motion induced flip between the 0 and 1 states of the qubit. You by now will have seen a number of these different IonQ-like systems. This one, of course, actually predates IonQ and provided the springboard at UMD for starting the efforts there. And it's worth pointing out some specificities of this system. It's based on a 32-channel AOM, so not acousto-optic deflector, which means that in principle, it allows parallel addressing of all qubits for parallel gates or very efficient quantum simulation. For example, recently, we performed experiments on continuous symmetry breaking in a trapped ion chain using this functionality in analog mode. Another feature or property of it is that the addressing beams are at 90 degrees, which allows them to talk to both ion modes this way, that way, or in the work that I'll be presenting here, we can orient the ion motional radial modes at 45 degrees and talk to this set. But in the future, you could imagine protocols where you push ions both this way and that way, such as, for example, following proposals in Norbert Linke's group, implement simultaneous XX and YY coupling in an Ising chain. Okay, so we want to implement this fault-tolerant readout of the Bacon-Shor code, which means if the first round of readouts flags, we should perform a second round. So we tested this protocol on one of the 2 types of stabilizers. So in order to do that, here is the mapping. We're reading out the X ancillas. and we provide a second copy of the x's. So we have 2x ancillas for round 1 and 2x ancilla for round 2. And we have our 9 data qubits to store the code state. Now, in order to work with this larger system, we needed to take care of one slightly technical problem that, however, also has quite a bit of bearing for quantum simulations on this platform. So what I'm showing here in dashed lines are the radial modes of these 23 ions. And what I'm showing in as heavy colored lines are the frequencies of the different gates, carrier frequencies of amplitude modulated gate waveforms that we're using. These short lines are a peculiar feature that you end up with when you work with long individually addressed chains. What is happening is you have a chain of ions, and you have these individually addressing beams. The chain of ions, being very long, is very susceptible to electric fields that cause it to shake along the axial direction. Now imagine that you're shaking back and forth while being addressed by a beam like that that produces a state-dependent force. Then from your viewpoint, the state-dependent force acquires sidebands at the shaking frequency. So these features here are sidebands of a tone 7. So if I apply tone 7, I will also inadvertently apply a tone here. If I apply tone 4, I will also inadvertently apply a tone 4 over there. And that can cause errors in the gates. These waveforms are not robust, they're not tailored, they don't control motion properly. So we chose for their gate waveforms the ones where these sidebands are detuned from the respective radial modes, which helped us a lot with the fidelities. Biggest reason I'm highlighting this is that the same story happens in quantum simulation regime, where one wants to operate very far detuned from all the modes of the chain. And when you do that, you are still encountering these sidebands, which are not detuned, but rather tend to perform gates that you never wanted to do. It's a very peculiar crosstalk effect. You want to run an easing, it works fine, and you have errors that are not Stark shifts, that are not dephasing, but that are actually somewhat clean YY interaction on top of an XX. Just another thing, always going back in atomic systems, we can understand our errors. Our errors are not simple decoherence. And once we understand our errors, we can tailor simulations and do things in a way that avoids them. So by using this good gate set, we performed the 2 rounds. And here, we compared the performance of different protocols for the Shor-style readout. The logical error rate, single shot, corresponds to just 1 round. Adaptive 1 method corresponds to what I just described. Adaptive 2, with a little bit of more analysis by Shilin Huang, working at the time as postdoc for Ken Brown, in collaboration with Shilin and Ken, they identified that this second round can be actually simplified so that in only one of the 4 cases do you actually have to perform the second round. And this fact lowers the errors that you get. I'm plotting finally in the blue line the use of this just as a detection code, similar to the recent work with many logical qubits in the Lukin group. So of course, if we only use an error correcting code for detection of errors, we get much lower logical error rates. Can we do better? These are pretty high error rates, order 8%. Can we decrease them? And indeed, a way to do that, when your raw gate error rates are high, was suggested already by Steane in '97. And the suggestion is quite simple. Take any logical qubit that you may want to implement and make a second copy of it. And then to do stabilizer readouts, you perform a series of parallel transfers, XX gates or C0 gates in general, between the 2 logical qubits. And this is straightforward to implement, and if you have enough qubits and have high error rates, as pointed out by Ken, in motivating us to try this out on the hardware, this should perform better than the usual stabilizer readout. So does it? So we tried it. So here we do encoding of our logical zero state. We perform the ancilla. If you want to perform one set of stabilizers, you will perform the ancilla in the logical zero state. In the other case, you prepare it in the logical plus state. And then you perform transfer C-naughts between them. And so here's the result. We see that by switching to the Steane code, now making use of our full system of qubits, we lower several times the logical error rates following syndrome readouts. And we lower the error, if this is used only as a detection code, to about 0.3%. So this shows that tailoring your code use to the errors that you have and to the number of qubits that you have available can pretty sharply reduce the errors. Still, I want to highlight the parallel work that explored a similar comparison across more codes by the Innsbruck group the same year. Also fault tolerant, similar to this work. Well, the errors on the previous slide are still substantial, and I want to challenge, can we do better? And of course, as I mentioned, there's single qubit dephasing. So for example, we have Z errors. The very most about 1.5% Z flip error across our full gate set. Most gates are significantly better than that, fully connected. But this is not the dominant error. The dominant error is due to something I already talked about. That this long chain of ions becomes very susceptible to electric fields that are shaking it back and forth this way. And the susceptibility of this ion chain increases with omega squared, where omega is the axial frequency. And this axial frequency in long chains roughly will drop as 1 over the number of ions. So if you're trying to address an atom or an ion with a focused beam, it could be a Rydberg atom, and that atom is moving back and forth with some energy E, then instead of experiencing the peak Rabi frequency, it will experience an average Rabi frequency. And that average Rabi frequency will be derated by an amount that depends on, this amount will depend on the occupation number of this oscillator. So the derating of the average Rabi frequency will be proportional to the excitation number of this oscillator, which means, given a Boltzmann distribution of the oscillator, that you will have an exponential distribution in the decrease of your Rabi frequency from the peak. Not Gaussian, exponential. It's quite a long tail. If you decrease the average Rabi frequency when addressing your atoms in a tweezer or in a long chain by 2%, you also have 2% noise. It's quite noisy. And so what can we do? We can cool the ions better, or atoms. We can confine them more strongly, or in order to lower this error. So far, the long chain systems that have been used have not had any sympathetic cooling that is well known in neutral atom systems or in ion systems that use two different species of ions, such as barium and ytterbium, for example, at continuum. If one tried to use barium and, for example, barium and ytterbium ions in a long chain, it was pointed out in the PhD thesis of Ellis and Carter in Chris Monroe's group at Maryland that this really severely impacts the connectivity of the chain. Basically, the ions that are of a different species do not participate in the modes of your qubit ions. So any gate that acts between here and here will have to contend with the gap between the two ions, which decreases the dipole-dipole interaction between the ion spins. A way to avoid that is to have near equal masses. And the platform that we chose is based on ytterbium 171 qubits, shown here in blue, and ytterbium-172 coolants. Usually, isotope shifts are not enough in order to achieve low crosstalk. However, ytterbium, due to its F electrons, is special. It gives us access to these states that have excited F electrons, which, when excited, result in scattered photons, which have very, very low crosstalk to the qubit ions due to short wavelength, narrow line width of the excited state, and large isotope shifts. So the full proposal and first realization is given here below. And we were able to demonstrate, while still at Maryland, that we can achieve cooling back to the initial axial temperature of the chain. Of course, another thing that you get if you can do cooling is you can do mid-circuit measurements. Because if you try to measure an ion, inevitably you need to scatter some photons. If you scatter some photons, that leads to heating, and you need to recool that to do gates. So ability to cool would also give us the ability to do mid-circuit measurements and continue performing operations, such as multiple rounds of error correction, or explore codes that involve mid-circuit measurements as a correction, explore phase transition based on mid-circuit measurements, and so on. One pesky problem that we had to contend with is that when you leave a chain of mixed species sitting in a room temperature chamber, if you just wait, they reorder. Just watch your chain, here's 172, 171. After 2 minutes or so, on average in our case, they will reorder. So Tianyi Wang, a graduate student in my group, in collaboration with Andrew Van Hoorn in Jung-Sun Kim's group, developed an algorithm to sort the chain. And the algorithm is actually quite simple. It runs in linear time. Here is our initial configuration that we want. Here is the final configuration. You look for the first position where the 172 ion is in the wrong position. And then you perform next neighbor swaps, like a bubble sort type swaps, to bring this ion to its correct spot. Then you find the next 172 ion. And then you perform bubble sort swaps to bring it into its correct position. You find the next one. You perform swaps to bring it there, and so on. And this runs in linear time. So does it work? Here's a demonstration. This is an actual experiment recorded on a camera. A chain is split multiple times in order to isolate eventually one pair, which is then swapped. So that's how we do this out of these swap primitives. And here is the same thing in action, data by Tianyi Wang. Here's the initial arrangement. The bright pixels correspond to 172 ions, the dark to 171. Time goes this way. And over 2 seconds, with 99.5% statistical success rate, we can sort this chain. And this is much faster than the 2-minute reordering time. So we're looking forward to controlled dissipation, partial measurements, much longer circuits, having countered this noise. I want to highlight, before I finish, a very recent application of the existing system to quantum simulation, so more RC2-like, in collaboration with Zore Davudi's group, and led with a lot of effort and great will by Niklas Müller, currently at University of Washington, who figured out, after a lot of work, how to efficiently pack the study of a thermalization of a Z2 lattice gauge theory on the available hardware. So the idea is that many systems by now have explored ground states and some excited states of a Z2 lattice gauge theory whose Hamiltonian consists of magnetic terms that are composed of plaquettes, highlighted in blue, and electric terms that are highlighted in red. What we wanted to contribute to the knowledge was to study the thermalization from various excited states of this lattice gauge theory and ask what is the evolution of the entanglement spectrum, that is to say, the spectrum of the logarithm of a reduced density matrix of a subsystem as a function of the evolution time. And what we have indeed, thanks to very efficient implementation by Niklas, been able to simulate this digitally on this digital machine and demonstrate the evolution from a Poisson distribution of the gaps between the eigenvalues of the entanglement Hamiltonian, so of the logarithm of the density matrix, towards a Gaussian unitary ensemble-like thermalized distribution shown at late times in panel 3 via an intermediate regime. This parallels the theoretical prediction that in large systems, the distribution of the eigenvalues should evolve from a Poisson distribution as a generic feature of such large theories through an intermediate generalized orthogonal ensemble to finally the same generalized unitary ensemble which our data is consistent with. And to our knowledge, this is the first study of thermalization of a gauge theory and a comparison thereof using hardware to the theoretical prediction. And so with that, I will highlight the last project that is being built up in my lab based on barium ions in a cavity that is also funded by the RQS. Please talk to me about it. There's some very exciting hardware and ideas for this, led by Jonas Tost and Erich Wette, two graduate students. Thank you.
Wonderful. Thank you so much for the talk. Do we have questions? Okay, I'll start. You said you were like doing these swaps in the sorting algorithm. How does that actually work in the ion trap? So how do you like move the ions around?
So the motion of the ions that you see here is performed by applying voltages to the DC electrodes of the trap. So quasi-static voltages. These produce little potential bumps that split the chain into several subchains. Once two ions are isolated, we squeeze them together. And you can imagine that if you squeeze them very hard, at some point, the frequency this way will become equal to the radial frequency. At that point, this ion crystal would be free to move sideways. So all you need to do is apply a little bit of torque, and then it will start to controllably swap. We do this near adiabatically. In this case, people like Mainz or Oxford do it mid-circuit, which they need to do for their platform. Of course, also Continuum. So here, a great advantage is we actually only need to do it offline during the reordering event. A thing I want to highlight here is that it requires fine-pitched electrodes that are usually only available in a microfabricated trap. This is not something that you can do in a longer chain, this protocol, in a big four-blade style trap that is used for in many quantum simulation experiments. So it is a clear example of an advantage from engineered traps, maybe not necessarily microfabricated.
Yeah, thank you. Sorry?
How do these ions
we assemble them one at a time. So we catch them in a separate zone of this trap. We bring them in and string them up like beads on a necklace, one at a time. Unfortunately, as you saw in as you see here, even during the reordering algorithm, every once in a while they get hit by a background gas molecule, probably hydrogen, which causes them to scramble. That happens during our initial loading as well, which takes typically about half a minute. So we usually do see these reorder events even during our assembly. In cryogenic systems, this is not observed. In cryogenic systems, the ordering is preserved. But I do want to highlight that even in cryogenic systems, the heating during partial measurement is still there. In atomic systems, the heating during partial measurement is still there. So if we're doing measurement, which we do by scattering photons, we need to counter the heating in all atomic systems. That's right. That's right. And we do this. And this is integrated then in every experimental sequence. It does shots. When it notices this, it throws an exception. It's an interrupt, totally computer science style interrupt. It runs the interrupt code and then continues. It's an example of CS tech.
Great, one more.
So does the heat map of error rates for XX interactions? Why is this?
This is, it's for an XX. Why are the Z's actually the same on both? I remember. I think I.
Oh, wait, maybe it is. Yeah, I was looking for bottom left.
I think, but I think physically during the XX gate, the two Z errors can be different. I think that here we took the average. That's a great question. Okay.
Okay, let's have one more question.
You'd need, I guess, few ways of doing damping is one can do it by charge coupling to the electrode, in which case you're thermalizing to the electrode. Electrode is room temperature, so that's a horrible idea. But let's say we're at 4 Kelvin. You'd thermalize to 4 Kelvin. Unfortunately, that's still quite hot for ions. This axial temperature in the bad case is about 20 millikelvin. So you'd really need this in a dill fridge for the direct coupling to the electrode to work. The other one would be feedback. But feedback, of course, causes photon scattering. You have to do it with very few photons scattered. Maybe, so cavity, something might work.
Awesome. Yeah, thank you. Thanks, Marko, so much again. Right, so we got to our next talk, which is a joint talk by Yikai Liu and Kaizhen Huang. Yikai is a computer scientist at NIST and co-director of QUIX, and Kaizhen is a grad student at UMD. And they will be talking about research on random pulse sequences for qubit noise spectroscopy. Looking forward to the talk.